I'd like a little video here about timers. So what are timers? Timers are basically for doing timing applications. System timing is a fundamental of real-time and embedded applications, and pretty much many applications require knowing the time. Main applications of timers are to generate events of a fixed time period, which can allow wake up from sleep or count transitional signal edges, replace delay loops, allowing the CPU to sleep between operations so it consumes less power, maintain synchronization clocks, debalance mechanical devices like switches. We use them for real-time clocks, like your watch has a real-time clock to know what time it is, actually. To control simulations, to measure rates. They're also used for keeping the speed right on synchronous communications. And they're used in analog to digital and digital to analog converters to maintain the timing so that the A to D or D to A converters measure at appropriate time intervals. Here's a block diagram of the MSP430F2274. And it has a bunch of different interesting features here. These are basically the I/O stuff is here, and so you can see there's several different clocks: A clock, SM clock, and M clock. There's flash and RAM and A to D converters and op amps and I/O ports and JTAG interface and emulation by SPI-wire and so on. There's also brownout detection, but the thing we're going to look at are the timers: the watchdog timer, the timer A3, and the timer B3. There they are right there. Let's first look at the watchdog timer. The MSP430 watchdog timer can be configured as a COP, also known as Computer Operating Properly device, or as a timer. Basically what the COP device is when a program can get frozen or locked up. The COP will notice that the watchdog timer wasn't serviced at a proper interval, and it will basically reset the processor, try and get things going again. You can also use the watchdog timer as a regular timer, as it says there. So the primary function of the watchdog timer is to perform the controlled restart after a software problem occurs. So after a power-up cycle, the watchdog timer is automatically configured in watchdog mode. User must set up or halt the watchdog timer prior to the expiration of the initial reset interval. Otherwise, the unmasked system reset is generated, which will start everything all over again. If the watchdog function is not needed in an application, the module can be configured as an interval timer and can generate interrupts at selected time intervals. Let's look at how we could configure the MSP430 watchdog timer. There's the basic register that controls this is WDTCTL, or Watchdog Control Register. And things that you can put in that register will tell you the interval of the timer, how long until it times out. You can do 32 milliseconds, which watchdog timer mdelay 32, or you can use mdelay 8 for 8 milliseconds, or mdelay 0_5 for 0.5 milliseconds, or mdelay 0_064 for 0.064 milliseconds delay. You need to write a watchdog interrupt service routine, and it needs to be callee safe, with a return from interrupt instruction at the end. You need to create a watchdog interrupt vector so that your watchdog interrupt subroutine gets called. In order to do that, you need to create in your assembly language a dot section, and that dot section for the watchdog, at least in the MSP 430 G2553, it's interrupt 10. You probably ought to double check that for our processor, the MSP 430 F5529. And in this section, after you've declared the section, you need to declare a word with the label name of where your interrupt subroutine, interrupt service routine is. So you'll see that in the next example. Then you need to enable the watchdog to interrupt. In other words, you need to allow it to provide interrupts for you. And you can do that by setting watchdog timer interrupt enable. So then you also have to do the global interrupt enable. So here's an example watchdog interrupt service routine example. So after initializing the stack, basically you want to configure the watchdog register. You need to set it so the mdelay is the right amount for you, and you need to initialize the watchdog timer counter. And you need to have an interrupt service routine, which is down here under the WDT_ISR label. And then you need your section for the interrupt, and put that word, watchdog timer _ISR, so it will know where to go when you get an interrupt. And you need to enable the watchdog timer to interrupt, both the global interrupt enable and the watchdog timer. You need to enable that. So here's another example. In this example, you configure the watchdog as a timer and enable it to interrupt right up here. And then we have a section that puts it to sleep, and it enables the interrupts simultaneously. And down here we have an interrupt service routine, which resets the counter every second, and it sets the active mode is saved in the interrupt service routine, and then afterwards it's after the interrupt service routine is left, it wakes up the processor. And you can see what this does is basically it allows you to sleep a long time, and you go and do something for a short time. In this case, you're toggling the LED at P10, but uses a whole lot less power, as you can see in the blue line below. So now I'd like to look at timers A and B. Timers A and B are the general timers, the ones you'd use most often. They don't have a special use like the watchdog timer. And Timer A and B, they're both 16-bit timer counters. They have 4 input clocks. You can pick between those. And some of them are fast and some of them are slow. That gives you a large range of timing capabilities. You can select what's known as the count mode. We'll talk about that. That's whether it counts up to a certain number, or it counts all the way up, or whether it continually counts forever and just wraps around when it needs to, or whether it counts up and then reverses the count back down. 1, 2, 3, 4, 5, 4, 3, 2, 1 kind of thing. These timers have just a host of interrupt capabilities. They're 3 capture and compare registers, which are very handy for setting the timers to go to a specific value. And they're also useful for making PWM. So let's look at the block diagram down here. We have a counter, a 16-bit counter. Basically, a counter is a logical circuit that counts up to a certain number, and it remembers the count. Then over here we have the clock source, which you can select which one you want to be used. This would be done with a multiplexer. And then we have a divider. The divider basically gives a pulse either every time the clock pulses, or every second time the clock pulses, every 4th time, or every 8th time. Basically, it counts by 1, 2, 3, 4, 8, and then wraps around kind of thing. We have over here the mode control, which can be up, continuous, or up, down, which hopefully you'll understand a little bit better as we continue this video. There's an interrupt that's set when the timer gets up to the place that you want it to. And that's the TA interrupt flag, timer A interrupt flag. And then there's a compare register, which you can use to compare and see whether you've got up to a certain number or not. And then that compare register controls some outputs. You can signal some external device when some amount of time has occurred. So the timers A and B are controlled by the T, either A or B, control register. This is a 16-bit register, and you can see at the top how its bits are allocated. And we're going to look at these bits and what they actually do for you. What do you do to set them, and what setting them do? So there's the tassel. Basically, it's the clock select bits, and those are bits 8 and 9. And you can decide which clock you want to use of the 4 clocks there. And so depending on what bit pattern you put there, it picks one of the clocks. Then over here on the right, there's the MCX register, and it's basically the mode. It tells you whether you're going to do stop mode, up mode, continuous mode, or up-down mode. Let's look at the modes so you can understand better what's going on with the modes. What are those up, stop, and all those things? So here is the up mode. The up mode counts until the count reaches the number that's stored in the TACCR0 register. When it hits that, then it rolls back to 0 and starts counting again until it gets up to there. And when the count gets up to the TACCR0 register, interrupts occur and those kind of things to tell you that happened. There's the up-down mode. And basically what it does is it counts up to the TA CCR0 register, and then it reverses its count back down. So that's like 1, 2, 3, 4, 5, 4, 3, 2, 1 kind of thing. And then there's the continuous mode, which just keeps counting over and over again up to the full value, which is FFFF, or 65,000 something or other, 2 to the 16th, basically, minus 1. So here's how the timer control registers are laid out in the MSP 430G2553. But they're similar in the MSP 430F 5529 that we use, but the actual addresses are different. You can see kind of a memory map over here on the right. Up at the very top is the interrupt vector table. And, that's where the ISR subroutine addresses are stored. And some of those go with the timers, some of those interrupts do. Then you have your program code, which goes up to that, which starts at the interrupt, or goes up to the interrupt vector table, starts at, in the MSP 430G2553, starts at 0xC000. And then there's the stack down in RAM. And then down at the very bottom of RAM, you have all the special function registers, and the first set of them is the 16-bit peripheral modules, of which the timer is one. So you can see all those control registers. There's a whole bunch of them. There's TACCR0 that it comes up to, and there's some other control registers that you can set as well, and there's the timer A control register, and the same kind of things for the timer V control register, and so you can see there's some registers for the watchdog down there too, less registers though. So here's another example. This is an example of using timer A. So in timer A, first thing you need to do is make some equates for the timer A control, and you set the tassel bit, which sets which clock you're going to use. You can set the ID bit, which tells what you're going to divide by on the divide by counter we talked about before, that goes into the into the main counter. You can select the mode here, in which case they've selected the up mode, mode 1, and then you enable interrupts. And if you look over in the comment there, it shows you what those bits are. Then down here, we often use these kind of timers for sleep. So we put the processor to sleep after setting up the timer. And then the timer A interrupt subroutine, which we need to have, wakes up, the computer wakes up and executes this when the timer A interrupt service routine is called. And first thing it does is acknowledge the interrupt, and then it toggles the P10 you see there. We also have a main part of the program here, which is jump $ means jump to this place, and it should never get there because we never take the processor out of sleep mode except when there's an interrupt. And down at the bottom you can see the section for the timer A interrupt service routine with the int 08. And it's probably a different number for the MSP 430F 5529 we use. And notice that in the interrupt service routine you have to clear the interrupt flag. Otherwise it'll keep coming back to this ISR. So here's a quiz for you. You need to figure out how you could speed up the blink. And what happens if timer A interrupt service routine doesn't acknowledge the interrupt. I'll let you work on this quiz here now. And we'll say that's enough for this video.